Imagine for a second that you're building the ultimate biological lock.
Yeah.
You've engineered this brilliant, intricate mechanism designed to completely shut down a hyperactive cancer cell. You deliver the drug, it clicks into place perfectly, and the tumor just stops growing.
Which is the dream, obviously.
Exactly, it's the dream. But then, right as you're watching, the cancer cell just calmly starts. Like 3D printing new keys. I mean, it physically changes its own chemical shape to break your lock and just keep growing.
It is, frankly, a profoundly frustrating reality. I mean, we usually think of a medical diagnosis as something static, Like you break your arm, the x-ray shows that jagged white line, and then the doctor just points and says, yep, there it is.
Right. It's broken. It's binary.
Yeah, and that binary is comforting to us. We want the problem to be visible, categorized, and then fixed.
But the moment you step into the world of targeted cancer therapies, that static x-ray machine just shatters. We're suddenly looking at a landscape that is constantly shifting. A lock and key aren't just moving, they're evolving.
It's the absolute definition of diagnostic muddy waters. And to navigate it, you really have to understand not just how a miracle drug works, but exactly how and why it eventually fails. Because understanding that failure at a microscopic level is honestly the only way we can build a better weapon.
And that exact evolutionary chess match is what we are deep diving into today. We got our hands on this really groundbreaking 2026 paper published in the journal Cell.
Yeah, a fantastic paper.
It really is. It's by Sang and colleagues, and it's titled Disrupted Molecular Glue Complex Drives RAS Inhibitor Resistance. So our mission for this deep dive is to unpack exactly how a highly promising new class of cancer drugs called molecular glues actually works. And we'll look at the ingenious and sometimes utterly baffling ways tumors evolve to break them.
And crucially, how scientists are already engineering the counterattack.
Right. We are going all the way down to the atomic level today.
It's structural biology at its finest, really. I mean, this paper gives us a literal atomic blueprint of an arms race happening right inside the human body.
So to understand how this drug works, we have to start with the target itself, right?
Yeah.
And that target is a protein called RAS.
Exactly. The RAS family of proteins, so specifically KRAS and RAS-NHRAS, you can think of them as the master cellular on and off F switches for growth and division.
Okay, so they're the switches.
Yeah, their entire job is to sit near the cell membrane and just wait for a signal. When they are bound to a molecule called GDP, that's guanosine diphosphate, they are perfectly quiet. The switch is off F.
Okay.
But when the cell actually needs to multiply, RAS swaps out that GDP for GTP, guanosine triphosphate. That extra phosphate acts as the trigger, so the switch flips on.
So GTP is basically the green light for cell division.
Precisely. And normally, a healthy cell turns that switch back off F the second the growth signal is done. It literally clips off that third phosphate.
Right, it unplugs the machine.
Exactly. But in many cancers, especially aggressive ones like lung, colorectal, and pancreatic cancers, the DNA code for RAS gets mutated. And the most famous culprits here are substitutions at the G12 position.
The G12 position. And what does that do?
This tiny mutation essentially breaks the switch mechanism. The protein completely loses its ability to break down the GTP.
Oh, wow. So it's like a stuck accelerator pedal. The green light literally never turns off.
Never. And when RAS is permanently stuck on N, it needs to transmit that signal downstream to the rest of the cell so it can divide. And it does this by physically binding to effector proteins.
Right, a family called RAF kinases.
Yes, specifically RAF, BRAF, and SHCRF. Now, the physical detail of how they connect is super crucial for everything we're going to talk about today.
Okay, lay it on me.
So RAS doesn't just casually bump into RAS to get the signal. It grabs onto it using two very specific grappling hooks. The first is called the RAS binding domain, or RBD.
RBD, okay.
The second is the cysteine-rich domain, or CRD. When RAS securely binds to both of these domains, it triggers RAF to pair up with another RAF protein.
And that pairing up is called dimerization.
Exactly. And that dimerization is what actually fires off the uncontrolled cancer growth signal.
Okay, so that handshake between RAS and RAF is the spark that starts the whole fire. So naturally, I guess the goal of cancer therapy for decades has been to physically separate them.
You think so? Yeah.
Which brings us to the drug in this paper, daraxonrasib, also known as RMC-6236.
Yeah.
But wait, hold on a second. Didn't we already celebrate solving this whole KRAS problem a few years ago, like with drugs like sotorasib?
We did. And, sotorasib was a massive historical breakthrough. But there is a really critical limitation there.
Which is?
Those older drugs are what we call O-off-state selective. They only bind to the inactive GDP-bound state of one highly specific mutation, the G12C mutation. They basically wait for the switch to briefly turn off, and then they lock it there.
Oh, I see. But daraxonrasib is different.
Completely different. It's a tri-complex inhibitor, or TCI. It targets the active on end state. And it doesn't just target one mutation, it targets multiple highly aggressive RAS variants while they are actively signaling.
Wait, how is it doing that? Because for the longest time, the active state of RAS was famously considered like undruggable, right?
Yeah, the classic undruggable target.
Because it's essentially a smooth biochemical bowling ball. There are no deep pockets for a traditional drug to just wedge into.
That's exactly where the molecular glue concept comes in. So daraxonrasib does bind to the active RAS protein, but by itself, it's tiny. I mean, it's not nearly big enough to block RAF from binding.
So what does it do?
Its true power is that it acts as a chemical beacon. Once it attaches to RAS, it recruits a natural protein that is already floating around in your cells called cyclophilin A, or CYPA.
Okay, CYPA.
Yeah, CYPA is what we call a chaperone protein. And daraxonrasib literally glues this CYPA protein directly to the mutant RAS.
It sounds exactly like a nightclub scenario.
How do you mean?
Well, mutant RAS is this hyperactive troublemaker, right? Trying to meet up with his partner in crime, RAF. But the drug, daraxonrasib, sneaks in and superglues a massive, bulky bouncer, the CYPA protein, directly to the troublemaker's back.
Oh,
right. And now the troublemaker is lugging around this giant bouncer, so they physically cannot get close enough to RAF to shake hands. The signaling just stops dead.
That is actually highly accurate. In biochemistry, we call that massive steric hindrance. The resulting tri-complex, which is made up of RAS, the drug, and CYPA, creates a physical barricade. RAF just bounces right off.
That is so cool. Okay, let's do a quick subtopic recap for you listening, just to lock this in. So bullet summary. First, RAS gets stuck in the on-end position, driving cancer. Second, daraxonrasib works by gluing a bulky bouncer protein, CYPA, to RAS. And third, this tri-complex physically blocks RAF from binding and sending the signal.
Spot on.
So here is a question for you, the listener, to chew on. Think about a time you tried to force two completely incompatible things together. How strong does a bond actually have to be to keep natural partners apart?
That's a great way to think about it, because keeping them apart is where the real challenge begins.
Right, which brings me to my next point. If this molecular bouncer is so brilliantly effective, why does the paper mention that out of 40 patients treated with daraxonrasib, 18 of them developed acquired resistance?
Yeah.
I mean, that's 45% of the patients getting sick again. The drug worked, the tumor shrank, and then the cancer somehow bypassed the bouncer. How did it do that?
Well, when the researchers sequenced the DNA of the tumors from those 18 patients, they found something incredibly specific. The cancer hadn't completely changed its overall identity. Instead, new microscopic mutations were popping up exactly at the 64th amino acid position on the KRAS protein.
Just one single position out of the whole protein?
Just one. Specifically, the amino acid tyrosine, which we denote with the letter Y, was being swapped out for either cysteine or aspartic acid.
Okay, so the Y64C or Y64D mutation.
Exactly.
But what does that tiny atomic swap actually accomplish? Like, why does changing position 64 suddenly render this amazing drug completely useless?
To understand that, we have to look really closely at how the glue actually works. It comes down to a phenomenon in structural biology called pi-p stacking.
Okay, let's unpack that. What exactly is pi-p stacking?
Think about the shapes of the molecules. In the normal, unmutated state, the tyrosine at position 64 has this ring-like molecular structure. We call it an aromatic ring.
Right, a ring of atoms.
Right. And the drug, daraxonrasib, also features a ring structure, an indole ring. When the drug approaches the tyrosine, their electron clouds perfectly align and magnetically stack on top of each other.
Oh, like two flat magnets snapping together.
Exactly, or like a perfectly stacked plate of pancakes. This pi-p stacking interaction is the primary anchor that allows the drug to actually hold onto the smooth surface of the RAS protein.
I see. And the mutation destroys that stack.
It does. When the tumor's DNA mutates and tyrosine is swapped out for cysteine or aspartic acid, the ring is just gone. The pancakes are taken off the plate.
So the drug loses its primary magnetic anchor point. Wow. It's literally like replacing a strip of heavy-duty Velcro with a slick sheet of Teflon. The drug is still floating right there in the cell, bumping into the protein, but it just can no longer grip the surface.
Teflon is the perfect analogy.
Well, wait, how do we actually know this is happening?
Yeah.
Because we can't just put a cell under a regular microscope and watch an electron cloud vanish, right?
No, absolutely not. We need something much more clever. And the researchers proved this using a brilliant piece of biotechnology called a split luciferase complementation reporter assay.
A split what? That sounds incredibly intense. How does that work?
It's actually really elegant. They essentially take luciferase, which is the exact same glowing enzyme that makes fireflies light up at night.
Oh, cool.
Yeah, and they genetically cut it in half. They attach one half of the glowing enzyme to the mutant RAS protein and the other half to the CYPA bouncer protein.
Oh, that is so clever. So if the drug is working normally, it glues RAS and CYPA together, which forces the two halves of the firefly protein to touch. And when they touch,
the whole complex lights up. You can literally measure the light coming out of a living cell. The brighter the glow, the stronger the glue.
that is wild.
But when they introduced the Y64 Teflon mutations into these live cells, the glow dramatically dimmed. It almost disappeared completely.
Because the proteins couldn't hold on to each other anymore.
Exactly. This proved, in real time, that the drug was failing to recruit the CYPA bouncer. The entire tricomplex was just falling apart because the Velcro was gone.
That is just incredible experimental design. All right, time for another quick recap. Bullet summary. First, 45% of patients developed resistance to the drug. Second, these Y64 mutations destroy the essential PIP stacking grip, the Velcro. And third, without that grip, the glue fails to recruit the CYPA bouncer.
Perfect summary.
So here's a question for you. If you were designing a drug, how would you even account for a target that can literally change its chemical shape to become slippery?
It's a daunting question for drug developers, for sure.
Right. But okay, so we've seen how the cancer can mutate to break the drug's grip. But what happens when the cancer doesn't touch the drug at all? Like, what if it just ignores the bouncer and forces its way through anyway? Because the paper talks about another mutation, the Y71H mutation.
Yeah, this is where tumor evolution shows its terrifying elegance. The Y71H mutation, which is swapping tyrosine for histidine at position 71, does not happen anywhere near the site where the drug binds.
It doesn't.
No. It has what we call an allosteric effect. It alters the protein's behavior from a distance without ever touching the drug itself.
But if it doesn't break the drug's grip, what is it actually doing? How does that help the tumor survive?
It alters how RAS binds to its natural partner, RAF. And to figure out exactly how, the researchers generated a 1.76 angstrom resolution crystal structure.
Okay, let's pause on that for a second. A 1.76 angstrom resolution. We're talking about freezing these proteins into a solid crystal and shooting X-rays through them, right, to map the diffraction patterns.
Exactly right. And at 1.76 angstroms, the resolution is so unimaginably tight that you aren't just seeing blurry blobs of proteins. You can see individual atomic bonds.
Wow.
You can see exactly where every single atom is sitting. And what they saw with the Y71H mutation was a neomorphic interaction.
Neomorphic, meaning a brand new physical connection that simply did not exist before the mutation.
Right. Usually when RAS and RAF connect, they hold hands, primarily relying on an amino acid on RAF called arginine 89 or R89. It's a really solid connection.
Okay, R89.
But the new Y71H mutation on RAS changes the shape just enough that it reaches out and grabs a completely different amino acid on the RAF protein arginine 67.
So it's grabbing R67 now.
Yes, and it forms a brand new hydrogen bond and what's called a pication interaction.
A pication interaction, let me make sure I have this right. That's when a positively charged ion is magnetically drawn to the negative electron cloud of a ring structure, right?
Yes, and
Yeah.
it creates a tremendously strong bond.
So it's like, imagine two people pulling a heavy door from opposite sides. The drug is the person on the outside, pulling the door shut. The cancer is the person on the inside, pulling it open.
I like this analogy.
The Y71H mutation doesn't do anything to weaken the person on the outside. Instead, the person on the inside suddenly grows a second, highly muscular set of hands. They haven't touched the drug at all. They've just multiplied their own native strength.
That perfectly captures it. Because the natural RAS-RAF connection is now supercharged with these extra neomorphic atomic bonds, the drug daraxonrasib is simply out-muscled.
It just can't compete.
Right. It's sitting there, desperately trying to wedge the CYPA bouncer in between them, but the RAS and RAF proteins are hugging each other so violently tightly that they cannot be separated. The strength of the natural bond completely overpowers the synthetic glue.
It really makes you think about problem solving, doesn't it? Like instead of fighting the obstacle directly, the cancer just strengthens its own internal foundation to the point where the obstacle doesn't even matter anymore.
It's a brilliant survival strategy, honestly.
Let's quickly recap that for the audience. Bullet 1. Y71H doesn't block the drug directly. Bullet 2. It creates a neomorphic, or brand new, interaction with R67 on RAF. Bullet 3. This supercharges the natural binding, totally outcompeting the drug.
Exactly.
So my question for you listening is this. Can you imagine a scenario in your own life where, instead of fighting an obstacle directly, you simply overpowered it by strengthening your own foundation? It's kind of a profound concept.
It really is, but it's actually the next finding in the paper that is perhaps the most mind-bending of all.
Oh.
Because breaking the drug is one thing, supercharging the bond is another. But the researchers also found patients who developed kinase-dead BRAF mutations, specifically a mutation called D594A.
Wait, hold on. Let's unpack this because it sounds like a complete paradox. A kinase is an enzyme that drives the cancer signal, right?
Right.
So if a mutation makes the kinase structurally dead or broken, meaning it literally cannot perform its chemical function anymore, how on earth is it driving cancer resistance? Shouldn't a dead kinase just stop the cancer in its tracks?
It is a total paradox. To understand why it works, we have to look closely at how BRAF proteins operate in the wild. You see, they don't like to work alone. In order to send a strong growth signal down the chain, they have to pair up.
Oh, the dimerization we talked about earlier.
Exactly. Now, these mutated, quote-unquote, dead BRAF proteins function as what we call obligate dimers.
Obligate dimers.
Yeah. Because they are completely chemically useless on their own, they are desperately forced to grab onto a healthy, unmutated RAF protein to form a pair. They literally have to piggyback on a healthy partner to get anything done.
All right, so a dead protein forces a healthy protein into a hug. But how does that stop our molecular glue from working?
Because the physical act of dimerizing the contortion of these two massive proteins locking together changes their overarching 3D shape.
Okay.
When that dead BRAF forces this incredibly awkward pairing, it twists the healthy partner. And specifically, it repositions that second grappling hook we mentioned at the very beginning of our deep dive, the cysteine-rich domain, or CRD.
Right. We said RAF uses two hooks to grab RAS, the RBD, and the CRD. So what actually happens to the CRD?
The twisting motion takes the CRD and smashes it completely flat against the RAS protein. It maximizes its binding surface, creating this incredibly tight, sprawling, suffocating grip across the top of the whole complex.
And the researchers actually proved that this specific physical grip is what blocks the drug, didn't they? They engineered something called the 3X mutation.
Yes, they did. They went into the lab and manually mutated 3 specific amino acids right on the CRD itself, L232A, F237A, and E275A.
So by doing that, they essentially filed down the teeth on that grappling hook so it couldn't grip smoothly anymore.
Exactly. And the moment they broke the CRD's grip, suddenly the molecular glue daraxonuracil worked perfectly again. The dead kinase entirely relies on the CRD's flattened grip to physically block the drug.
You know, it sounds exactly like a zombie.
But a zombie.
Think about it. On its own, the zombie is dead and completely incapable of opening a door or causing targeted damage, right? But it blindly grabs onto a healthy person, dragging them down, and their combined, awkward, sprawling weight completely blocks the doorway, keeping our molecular bouncer out.
That is precisely what is happening at the molecular level.
The dead protein is actively weaponizing its own brokenness to create a physical barricade.
It forces a structural conformation that just locks out the drug. If you remove the CRD's grip, if you take away the zombie's weight, the whole barricade falls apart.
What a terrifying testament to the resilience of biology. Okay, let's recap the zombie paradox. Bullet 1. Dead PRAF kinases are forced to pair up, or dimerize. Bullet 2. This dimerization twists the CRD domain into a tighter, sprawling grip on RAS. And bullet 3. This tight grip physically blocks the glue from working.
That's the mechanism in a nutshell.
So listener, ask yourself this. What's it tell you about the resilience of biology that a broken, dead protein is actively used as a weapon for survival? It's just wild.
It really is.
So the ultimate question is, how do scientists fight back against an enemy this adaptable? We have a tumor that acts like Teflon, grows extra hands, and weaponizes dead proteins. Where do we even begin?
We begin by adapting right back.
Okay, I like the sound of that.
Let's start with the Y64 Teflon mutation, where the drug lost its magnetic pi-p stacking grip. During the early development of daraxonrasib, the researchers hadn't just made one chemical. They had tested entire libraries of different structures.
Right.
So they went back to that library and pulled out an analog called RMC-4791.
And how is RMC-4791 structurally different?
It finds a completely different handle to grab onto. Remember how daraxonrasib relied on perfectly stacking its center ring on the tyrosine at position 64?
Yeah, the pancakes.
Right. Well, RMC-4791 doesn't care about position 68 at all. Instead of grabbing the center, it engages the RAS protein using its tail end.
Oh, so because it doesn't rely on that broken pi-p stacking interaction?
Exactly. The mutation doesn't matter. It successfully glues the CYPA bouncer to the mutated RAS anyway. The Teflon is totally useless because the new drug is grabbing a completely different part of the surface.
It just bypasses the defense completely. That is brilliant. But what about solving the zombie BRAF situation? Because that massive CRD barricade seems much more complex. I mean, you can't just change the handle on the door if the entire doorway is physically blocked by two heavy proteins.
No, you can't. For the zombie barricade, the solution isn't a new glue, it's a tag team approach. It's combination therapy.
Ah, okay.
The researchers found that if you combine our original glue, daraxonrasib, with another type of drug, specifically a dimer-disrupting RAF inhibitor, or a drug that targets the signaling further downstream, like an ERK inhibitor, you can actually reverse the resistance.
I see. So you send in a drug specifically designed to break the zombie's grip on the healthy protein first.
Yes.
You shatter the dimer.
Yes.
And once that pair is broken apart, the sprawling CRD barricade collapses, the door is finally open, and our molecular glue can get in and finish the job. Time for our final recap. Bullet summary here. First, RMC-4791 bypasses Y64 mutations by gripping the tail end of the protein. Second, dimer-disrupting drugs break the zombie BRAF resistance. And third, combinations are definitely the future of this fight.
Absolutely.
So if you were a doctor, would you try to predict the cancer's next move and give the combination therapy up front, or wait to see how it mutates? That's the real clinical dilemma, isn't it?
It is. If we zoom out and connect this to the broader picture of oncology, this is the stark reality of targeted therapy. It is an iterative, unending arms race.
Right.
We see this with gatekeeper mutations in lung cancer and leukemia all the time. We design a brilliant drug and the cancer mutates to block it, but now we can map that exact microscopic mutation structurally. We can see the atoms.
And we use that map to design a second-generation drug.
Or a highly specific combination of drugs, yeah. We try to bypass the block before the cancer has time to catch its breath.
It's biological whack-a-mole, but played with supercomputers and X-ray crystallography. It really is a marvel that we can even observe this happening. Molecular glues like daraxonrasib are genuinely revolutionary. I mean, they are successfully drugging the undruggable.
They are.
But we have to respect the opponent we are up against. Native protein interactions like that handshake between RAS and RAF have been forged by literally millions of years of evolution. They are fundamental to biology.
They're hardwired.
Right. And when we try to permanently keep them apart with a synthetic glue, the cell is going to use every single trick in the book, slipping out of grips, supercharging native bonds, even resurrecting dead proteins, just to reconnect and survive.
And this paper by Sang and colleagues proves that we finally have the tools to watch them do it, atom by atom. We aren't just blindly guessing why a clinical trial failed anymore.
We can see it.
We are watching the tumor build the new key in real time, and we are actively designing the countermeasure before the tumor even finishes the job.
It's a breathtaking shift in how we approach medicine. So as we wrap up our deep dive today, I want to leave you with a final, slightly provocative thought to chew on. We started by talking about biological locks and keys. As we engineer smarter drugs moving rapidly from daraxonrasib to RMC-4791 and beyond, the tumor invariably engineers smarter locks.
It always does.
So are we destined to be trapped in an eternal game of biochemical chess with cancer, continually inventing new, slightly better molecules just to stay one single step ahead? Or will we eventually uncover some fundamental vulnerability, a universal glue that checks the king and checkmates this system once and for all? That's something for you to mull over today.